So the next talk is pre-recorded. It's going to be given by Evgenii Moiseenko, called Relaxed Memory Concurrency Re-Executed. It is also a paper that received a distinguished award in this POPL. I believe Evgenii will be live with us after the talk for questions.
Hello, my name is Evgenii. And I'm going to present our paper, Relaxed Memory Concurrency Re-Executed. So first of all, let me briefly introduce the topic. Memory model of a programming language defines what values reads from shared variables can observe in a concurrent program. Memory model is called relaxed if it permits non-sequentially consistent outcomes, that is, outcomes that cannot be obtained as a result of simple interleaving of instructions from different threads. Such outcomes can typically arise as a result of some optimizations performed by the compiler or the hardware. So for instance, if we take a look at the program shown on the slide, we can notice that an optimizing compiler can reorder two independent instructions in the left thread. After this, the outcome where a equals b equals 1 can be obtained as a result of interleaving of instructions. It means that this outcome is an allowed relaxed outcome of the original program. Defining a relaxed memory model has been a long-standing challenge because it must balance two conflicting requirements, performance and programmability. For performance, the model should be weak enough to support all the desired optimizations. However, if the model is too weak, it can accidentally allow so-called thin air values. So if we take a look at the another program shown on the slide, we can see that an outcome where a equals b equals 0 is a valid outcome of this program. On the other hand, an outcome where a equals b equals 1 is a thin air outcome because no reasonable compiler optimization can enable this outcome. Yet, the current formulation of the C-memory model called C20 technically allows this outcome. So the C20 model has this thin air values problem. In order to forbid thin air values, researchers propose to strengthen the model. The resulting model is called RC20. But it turns out this model is too strong because, unlike C20, it does not support optimal compilation mappings to hardware, and it does not support all the desired local program transformations. To see why it happens, we need to have a deeper look at the details of these models. Relaxed memory models are defined in axiomatic style, axiomatically in pre-execution style using so-called execution graphs. Nodes of this graph represent various events such as read or write accesses to the memory, and the edges in these graphs form various relationships between these events. Most notably, gray-colored program order edges represent syntactic order between the events, whereas green-colored reads from edges connect each read event to a single write event from which it takes its value. Semantics of the program is defined as a set of execution graphs, and the memory model defines what execution graphs are consistent. So, going back to the examples, if we consider a program on the left and all its possible execution graphs, the C20 memory model considers all of them consistent. On the other hand, the RC20 model considers only the left graph as consistent. That is because RC20 is basically C20 consistency plus an additional constraint requiring that the union of program order and reads from relations should be acyclic. But it turns out that this additional constraint is too strong, because if we take a look at the program on the left and consider all of its possible execution graphs, then again C20 considers all of them consistent, but RC20 considers only two of them on the left consistent. However, in this case it poses a problem because this third cyclic execution graph actually corresponds to a valid outcome that can be obtained as a result of instruction reordering. Can we prevent thin air outcomes while maintaining compilation efficiency. In our paper, we address this challenge by proposing a novel memory model called XMM. XMM eliminates thin air outcomes while supporting efficient compilation and local program transformations, such as instruction reloadings and instruction eliminations. As such, the first contribution of our paper is a novel axiomatic operational semantic framework for relaxed memory models, XMM. The XMM framework builds on a given axiomatic per-execution memory model. It extends the given memory model with out-of-order re-execution capabilities, enabling efficient compilation while forbidding thin air outcomes. We instantiated the XMM framework with the C20 consistency constraints to arrive at the model, which we call XC20. Next, let me explain how XMM works using some examples. The XMM has two operational rules to construct execution graphs. The in-order execute rule at each step adds one program order and reads from maximal event to the graph, and it ensures that the resulting graph remains consistent. Whenever a read event is added, it must be connected to an existing write event via reads from relation in order to prevent thin air reads. However, the execute rule alone cannot create cyclic graphs. This is why we need another rule. The out-of-order re-execution rule enables creation of cyclic graphs. It works as follows. Given an already constructed graph, it selects a subset of committed events of this graph, and then it rebuilds the graph while preserving the committed events. Similar to the execute rule, it ensures that the resulting graph remains consistent. Importantly, during the re-execution, it is allowed to add a read event that reads from nowhere, but only as long as it is committed. This constraint prevents thin air reads by ensuring that the values of committed reads are grounded by the original execution, and the writes from which they read from are guaranteed to be restored in the resulting graph. With the help of these two graph construction rules, XMM achieves no thin air, optimality of compilation mappings, and soundness of local program transformations. However, we must admit that XMM is not the first model that attempted to fix the thin air values problem. In fact, XMM was inspired by the Java memory model that was based on similar ideas. However, our model avoids the pitfalls of JMM in supporting desired optimizations. Previously, the research community also proposed the operational premising semantics, the Wikistema model based on event structures, as well as some other notable models, which we do not mention on this slide due to time and space limitations. These models are commonly referred to as multi-execution memory models, and they also avoid thin air values while supporting desired compilation properties. So what makes the XMM model stand out? To answer to this question, we need to look at another important program transformation, thread sequentialization. Sequentialization merges two threads into one. Let us look at some example. Firstly, in this example, the second thread can be merged into the first thread. After this, following the conditional assignment to variable x, the read from x in the last statement always returns 1. Next, the assignment to variable 1 can be reordered above in the resulting program, and interleaving where instructions of the second thread are executed in between instructions of the first thread leads to a relaxed outcome where a equals 1. Thread sequentialization is sound in C20 and RC20 models. However, it isn't sound in the multi-execution memory models. In XMM, we fix this problem, and in our model, thread sequentialization is also a sound transformation. This is the second notable contribution of our paper, as XMM is the first model to support thread sequentialization along with other desired properties. To showcase how exactly XMM supports thread sequentialization, let us go back to the example. The key here is that, unlike previously proposed multi-execution memory models that allow execution of only a single thread at a time, XMM allows execution of several threads. The only requirement is that threads should be re-executed one by one in accordance with a chosen thread ordering. So, to justify the relaxed outcome where a equals 1 for the given program, XMM first constructs an acyclic graph shown on the slide. It then commits events E4, E5, and E6. After this, it re-executes the program, constructing another graph. Construction starts by adding events E5 and E6 prime, and then it proceeds to re-executing first and second thread one by one, in accordance with the thread synchronization ordering. So in this way, XMM supports the thread synchronization transformation. XMC has another advantage over previously proposed multi-execution memory models. It is amenable to automated reasoning in the form of model checking. So first, let us have a look at the situation with other models. Scene20 is basically not checkable because of the thin air reads problem. On the other hand, the problem of model checking under XC20 is relatively well studied, and there exist a lot of tools. But these tools rely on the acyclicity of execution graphs. The problem of model checking under multi-execution memory models was untackled until very recently. A tool was proposed for the weakest memory model, however, it was not proven sound. So the third contribution of our paper is that we developed XMC, a sound model checker for the XC20 memory model, and we proved its soundness. XMC was developed on top of the state-of-the-art GNMC tool. Given a program, GNMC explores all its RC20 consistent executions. To construct these executions, GNMC relies on a procedure resembling the execute rule of the XMM semantics. At each step, it adds single maximal event and checks that the new execution graph remains consistent. Thus, to generate cyclic executions, the challenge was to extend GNMC with a procedure implementing the re-execute rule. However, in its general form, the re-execute rule exhibits significant non-determinism. It can be applied at any step with an arbitrarily chosen set of committed events. To tame this non-determinism, we have developed a strategy that implements a restricted version of the re-execute rule, making the model checking tractable in practice. To this end, we use a heuristic based on load buffering races, specific read-write races, with a program order and reads from path from a read to a write event. When a load buffering race is detected, the algorithm deterministically identifies committed events, and then it performs re-execution. In our paper, we show that XMC works reasonably well in practice and is capable of verifying realistic benchmarks, in some cases with the performance comparable to the baseline GNMC model checker. We refer to our paper for a more detailed evaluation. So in our paper, we have proposed XMM, a novel semantic framework for relaxed concurrency. Unlike its predecessors, XMM is defined in almost a pair execution style, making it potentially easier to integrate with existing specifications. For example, the C language specification, which is also given in a pair execution style. Moreover, XMM is the first model of its class that supports thread synchronization transformation in combination with local program transformations, such as instruction reordering and instruction elimination. And finally, XMM is also amenable to automated reasoning. Yet there is still much work to be done. First of all, we are currently working on the work mechanization, and we have already proved some of the model's properties in this proof assistant. Next, we are planning to support sequentially consistent accesses in the model as standalone primitives to support the full range of the C language features. And finally, we aim to achieve completeness of the model checking algorithm and to prove it formally. So to conclude, XMM is a novel axiomatic operational semantic framework for relaxed concurrency. It solves the thin air values problem, supports optimal compilation mappings to hardware, local program transformations, and sequentialization transformation. Moreover, it is amenable to automated reasoning in the form of the model checking. Thank you, and I'll be happy to answer your questions.
Okay, we have plenty of time for questions. Is Evgenii with us live? Student volunteers? We have? Okay. 1, 2, yes. Yeah, 1, 2.
Yes, hello. Can you hear me?
Yes, can you? Who has a question? I saw a hand raised earlier.
Hello, Evgenii, it's Victor here. It's a very nice piece of work. I would like to ask you, what is the main difference between your model and the Java memory model, which also has this re-execution idea?
Yeah, okay. Sorry, I don't.
I'll repeat the question, maybe it's not audible. So the Java memory model of Manson and other had the similar idea of committing some events and adding some more and some more. So what is the main difference that makes your model work and the JMM not work?
Yeah, sorry, I didn't hear out because I have an echo. Let me.
One more time.
Can you hear me?
Yes. What is the difference between your model and the Java memory model? In the sense, the Java memory model has a similar strategy as yours, but somehow the Java is broken and yours is okay.
Yeah, can you hear me? Because I think there's some technical problem.
We can hear you.
I mean, I heard the question, but when I start speaking, I also.
Yes, we can hear you.
Okay. Yeah, just when I start speaking, I hear myself. So okay, I'm going. So the question was, what's the difference with the Java memory model, which is based on similar ideas? I think the differences, like yes, I said it's the idea is similar, but the difference there's a lot of like technical differences in a way how we commit the events, for example, and what's the rules of the committing events. So, for instance, in one of the most significant differences in the Java is that whenever they commit events, the committed events like they are preserved through whole construction of the graph. Like once you commit an event, it's always committed. Like you cannot make one re-execution step with one set of committed events and then make another with another committed events, because like the committed events must be grow monotonically in Java memory model. We also tried this at first in our model, but we realized that this like doing this naively doesn't work. So we had more relaxed rule, like we allow basically dropping committed events in terms of Java. And there were also a lot of other technical differences with respect to what constraints we put on committed events. So for example, one of the issues with Java was that they were requiring that the program order between the committed events should be preserved, but it is too strong for reordering. And that's, for example, we have a more relaxed constraint when instead of program order, we use a special like subset of program order, which we call relaxed program order, that basically only the program order that is enforced by fences and like release, like acquire release events. So it's really hard to answer the question without going into too much detail. So yeah, but basically the answer is that there's a lot of technical details in how we handle committed events.
Okay, thanks. Any other questions? So I have one, if you can hear me. So when you talk about soundness and completeness of your model checker, how do you define that? Is that with respect to bug finding or with respect to the executions that you explore? What does soundness mean?
Our terminology is in terms of executions we explore. So by soundness, we mean that every execution graph that we generate is XC20 consistent. Yeah, so that's, and in this sense, yeah, we do not claim completeness because basically, yeah, we do not like know if like it is if like it is possible to enumerate any like consistent graph. It's actually like quite complicated problem.
And in the same context, is there any notion of minimality in your exploration, or could you be exploring the same execution multiple times?
No, unfortunately, there is also no minimality here. Like, yeah, unlike like basic GenMC algorithm, which guarantees minimality for RC20. Again, there's, because of this cyclic execution graphs, the problem becomes much more complicated, and we do not know yet any way how to kind of ensure minimality, or even if it's possible.
All right, thank you. Any last questions? No? Okay, so let's thank Evgenii live.
Thank you for having me.